What's up, my fellow hackers, makers, breakers, thinkers, tinkerers, solderers, modderers, and just downright technically inclined deviants? And I say that with the utmost respect because I consider myself to be a technically inclined deviant. My name's Digital Andrew, and I'm here with another IoT and hardware hacking video. This video is going to be a continuation of the series we've been working on where we're learning about chip-off firmware extraction and modification. So if you haven't checked out the first two videos in this series, I'll drop links down to them below, and I highly suggest you check those out where we go over how to do chip off firmware extraction and how we got the firmware that we're going to be using in this video. And then also how I like to use a test jig when we're doing chip off firmware work to be able to write a bunch of different times firmware to the chip without having to keep soldering it on and off. That's in the second video, so I'd check that one out as well. In this video, we're going to be covering the software side here, where we take a look at extracting out the firmware, finding the portions that contain what we want to modify in order to accomplish our goal, which in this video, to make it interesting, is going to be to put a backdoor into the router so that it reaches out to some command and control infrastructure. And then I'll go over all the steps that you need to do for this router, and I'll try and make it as generic as I can for other devices to actually then go and put that firmware back all together in the format that it needs to be to actually be able to properly flash it on the chip and get that device booting, because it's not just as easy as modifying a few scripts or, putting your own binary in. There's a lot of different things you have to take into account with embedded systems to be able to get everything to boot properly. There's lots of quirks with embedded Linux, and I'm going to try and cover how to check for those things and make sure that you're packing it up properly. So with that being said, let's hop over now and dig right in. So first thing we'll need to do is something that probably a lot of you are familiar with, but if you aren't, I will go over the steps quickly, and that is to use binwalk to actually unpack that firmware. We've got it here. It's this original firmware.bin here, and it's just in this data format. So in this format, we can't make any modifications or really do anything to it unless we want to modify the raw hex bytes, which that is outside of my level. So what we're going to do is use binwalk to carve this out. So we're going to go binwalk, and then it is going to be -me. So M is for recursive, telling it to recursively go into all of the folders and files and keep extracting it until it's down to like a format that's no longer extractable, like a .sh or .txt. And the E is just telling it, don't just look at it and identify it, but actually extract it out for us. So we'll let this run through. We can see here, it's found a whole bunch of different parts of the firmware that it has carved out for us. And it has nicely placed it in this underscore original firmware.bin.extracted. So the next thing we need to do is figure out essentially what our goal is or what we're trying to accomplish with this firmware modification. And what I want to show in this one is just something that's high impact to demonstrate why you may want to consider using secure boot, or at least, locking down your firmware and boot process a little bit more, which we'll see in this. There's really nothing preventing putting custom firmware. So what I'm going to be going for is, again, putting in some C2 infrastructure to have a back shell. So to reach out to our infrastructure, we'll put a client in here or an agent to reach out to some C2 infrastructure. So for us to make that, the easiest way for us to put that in is just to modify the root file system. This is where all of the things like the binaries, the libraries, the scripts, the configuration files, all of that stuff, if you just went, into a regular Linux computer and you looked through the file system, all of that stuff is the root file system. So we're going to be modifying that. And generally when I'm doing firmware modifications, that's what I'm going after. But it is also possible to potentially try and patch the kernel or modify the bootloader itself if that's what you're going after, but that's a little bit more of a complicated topic. So we're going to start with the root file system. On this router, it is in the format squashfs, the file system. So this is a type of file system that is heavily compressed read only. So when this is pulled off of the flash chip and into memory, it's set up as read only. We can't actually change this on the device and have anything persist on it. So what we're going to do is actually go through this and take a look at where we can, make some impactful changes. So one of the first things I'll like to do just to make sure everything's working and that I have all the packing down properly and how we, zip this back up and everything like that is I'll just make a little change to something that's easy to see. So one of the things I like to do is just modify one of the init scripts. And embedded Linux, usually it's going to be using the BusyBox init system with init.d. So usually you're going to have inside of the etc folder an init.d folder, and then you're going to have these RCS scripts. So on this one, it's just got one. So this script's going to be called very on in the Linux boot process after the bootloader is handed over to Linux. So what we could do is go in and add in our own little echo command or something that just, says we were here. So before we do that though, instead of messing around with, what is our original one, what I'm going to do is I'm actually just going to copy this and then maybe paste it in here. And then I'm going to rename this here and we'll call this something like maybe patch underscore RFS. So let's take a look at the RCS in here. And then what I like to do is go and find where there starts to be some echo commands here. And then what I'm going to do is I'm just going to add my own. So these will be printed out in the UART session. So we can go and I'll just add one here. I'm going to go like echo, and then we'll just go digital Andrew was here. Perfect. And then we'll save this. And now we've made just a really small modification here to this file. And we can go take a look at now how we can pack this all up and flash it back on. So what I like to do when I'm packing up firmware is I actually have a checklist that I go through of the things that I just need to check over, make sure I understand and know the details about before attempting to pack up firmware. So I've actually got a checklist here, and if you want access to this checklist, and also I've then gone ahead and just written a script for this firmware, but that you could definitely reuse for other firmware as well with a little bit of modification. I've written a script for this just to make it way easier when you're doing testing. It's nice to be able to just make a quick change and then run the script and have it take care of all this for you. So if you want access to these, I'll drop a link to a GitHub repo down below. That's actually for all of my testing notes and everything from the IoT and hardware hacking course in that repo. And you can grab those from there. So let's quickly go over the checklist here. Again, I like to go over this because I always forget things. So I've just created this, over time. And this one's specific to this router, but you should be checking most of these things. So we've already done this one. Again, if you're doing like a proper test, it's good to make sure you're keeping track of the MD5 or some other type of hash. So you know what sample you're working on, that it's matching. We'll then want to go and identify the root file system type and compression. So the type of compression is really important. Not only just is it squashfs, but there's also flags for what type of compression is being used in the different file systems. So squashfs is a common one. You also see like JFFS2 as well commonly. So let's go ahead and just run that binwalk. So we're actually just going to we won't run the compression here because we're going to there's a few failure messages and stuff in the compression. So we'll run binwalk, and then it's just going to be on the original firmware.bin. And we won't extract it here, but we can see this squashfs file system. And we actually get some details here too that we're going to need. It's little endian, and we can see the compression is XZ. The size is this many bytes here. What is this? 202,997,270 bytes. And we can also see the start and end of this as well, which is going to be important for us to keep note of. So here we see again, squashfs, we know which version it is, compression, the block size, 256 kilobytes, and the endianness. So we could also extract and do this manually as well. So if we use DD to carve out, we can extract it as well. And then the other thing we'll need to do is identify the decimal and hex offset where these begin, which we get that from squashfs. We have it here. This is going to help us know when we pack this back up, when we recreate our squashfs, where do we put it back into this firmware.bin. We then need to determine the total size of the firmware flash chip. So we need to know how big it is so we know how much space we have, and also so we can make it back to that size. Because sometimes if it's not, the exact size that's expecting, that's also going to cause issues as well. So this is, just a little bash foo or Linux here. We can just run this, and this is going to tell us the size of that. So we get this, it's about 4 megs here. So we don't have much space to work out. Next thing we'll need to do is calculate the maximum size of the root file system. So we know, do we have much to work with? Are we able to, expand this? So we're just using those offsets here. So I've got some math here as well. Okay, so we have a little bit of space to grow here. We can see this is the maximum size that we can grow to. The next thing we need to do is make sure that all of the device nodes exist in the root file system. So if you're using binwalk to extract this out, and especially if you're not doing it as root, it's just going to drop all of these device nodes, and it will drop it silently. So when you take a look at this squashfs root, for example, if we go in dev, there's nothing. So those nodes to things like dev null and TTY and things like that, those are all going to be missing. And then potentially that's going to cause issues on the boot. So one way, I'll do this is some of it's trial and error. Like you'll boot and you'll see, kernel panic caused by certain things, and hopefully the logging's good enough and you can figure that out. But from having done this enough times, I know to also look for this. So again, we can use unsquashfs here on this, and maybe we'll just run it on the patch rootfs here, or maybe we can do we have it? What's it called here? The actual squashfs is here, 1000.squashfs. So let's run this here, but this is actually going to be here. If we get rid of this, we'll do this on the 1000 or 100,000.squashfs here. So this is going to be underscore original. Perfect. And then this is going to be like one. Perfect. And then we can just get rid of this actually. And so what we're grepping for is these C's, which show that these are the character devices. So you can see we've got like dev console, null, random, TTY, all those stuff you would expect to see in Linux. So if we take a look in ours, they're all missing. So without those, we're going to get kernel panic. So we'll need to check for those and then be able to add those in. And then we'll need to create those. So if we're missing, we'll need to go ahead and create them all. Again, we're going to remove anything of the old ones, and then we repack the squashfs file system. So this is all the manual stuff. What I'm going to do is just quickly go over and show how my script works here that I've written. The main thing I want to show in that checklist is, if you're modifying the script, how do you know what parameters to put in here? So again, we do some just basic error checking, see if the script or the original firmware is still there. Remove the old stale squashfs to avoid, remaking another one. And then we go in and create those essential device nodes if they don't exist. So this is where it actually then creates those ones we just saw to make sure that they are there. We then make a squashfs file system with that one that we extracted. So we're looking at patch underscore RFS. And then we turn that into a squashfs file system. You'll see here, so this is where that compression time and the block size is. So we're matching up to what we found previously. And then we check and make sure that we're going to have enough room. So we're allowing just a little bit of extra room here, but to make sure that we're not going to be going over and exceeding the space that's allowed, because then we're going to start overwriting into stuff that's going to make it not work properly. And then what we do is we take a copy of the original firmware and we call it patch firmware. And then at that point we use DD to slice in our squash FS. We're patching this in, and you can see here, like this is where the seek is where we're starting. So this is where the old one started, and we're just using a block size of 1. So this is essentially taking our squash FS that we created and stitching this into the original one, overwriting the bits that are in there with the ones from our squash FS, and this block size and seek is telling it, how to write those and where to start. We then do a truncate, and what this is going to do is make sure that it's not longer than the size it should be, and if it does, it will actually pad it for us as well to make sure that it matches the right size and everything. So again, if you want to copy this script, go ahead and take it from my GitHub. Feel free to modify it, reuse it as needed. Just the one important thing I want to go over is if you're wondering, like, where do these values come from? How do you know them? That's from the checklist and the things that we check. Okay, so at this point, we got our patch RFS ready. We can go into utils and we can actually just run this. So let's head over there. And now let's run /pack. Is it pack? Yeah, pack. Oops, pack. And let it rip. Again, need sudo for this to be able to create those device nodes. Perfect. And we can see that it's succeeded. And now we have this patch_firmware.bin. Okay, so we've got our firmware all patched up. Now at this point, we can write it onto that chip. So I've got my XGECU hooked up here, and I've taken out that jig, or taken out from the jig the adapter, popped it in, and we can attempt to now write this. So I'm going to be using Mini Pro again for this. I showed it in the last video, but essentially instead of reading now, we're just going to be doing a write here. So again, we figured out last time, the actual device name for this chip. So if you're wondering how to do that, that's how we figured that out. And then instead of -R for read, we're going to be doing -W for write and specifying the file that we want to write. And again, I got this -Y here just to skip the checks, because for whatever reason, I don't know why Mini Pro can't seem to read the identifier from this specific chip, which is a check that it does to make sure it's talking to it properly, but it works without it. So sometimes I just run that skip and it still works. And for this one, it does. So I'm just going to run that right now. We'll let it go through. You can see here it's saying, yeah, it's got this mismatch, ID mismatch, but that's okay. It's going ahead and erasing here. So we'll just let it run through. It's now writing the code to it. And then afterwards, it does a verification, which is nice to make sure the integrity of, the code matches what was there before. Perfect. So the verification's good. So what it's doing is then matching that, what it wrote to it matches what it was supposed to write, that we didn't have any flip bits. So we've got it written there. So now what we can do is I'm going to hook up the UART, the USB to UART adapter. We can boot this router and see if our modification stuck in the boot logs, and also make sure, afterwards everything boots properly. We didn't break anything. So let's run screen here, connect to our UART USB adapter, and then I'll fire on the router, and we can see if it actually boots and if we are actually able to see the change that we put in here. Okay, perfect. We can see the boot logs coming in through here. We'll let it hand over to the router here, and looks like it is still booting here. So let's go ahead and take a look if we are actually able to then see once those echoes come through. Let it finish its whole boot process, and then we should be able to just take a look here. Let's see, actually, yeah. So it's generating the key. So let's go to scroll mode here and then take a look and see if we can't find Digital Andrew was here. So if we keep scrolling here till we get to where the Linux kernel is starting here, we can actually see where it is calling that RCS, and then perfect. We can see Digital Andrew was here. So it looks like our modification took place. And then if we get out of copy mode here and then we get in, like we can see, we are in shell router is booted up with our modification here. So what I'm actually going to do is end this video here, and we'll make a part 2 to this one where I'm going to go over the actual command and control infrastructure and writing in the back door, because I want to make sure that I have time for actually covering the details of that, because I think it's quite interesting, and I think you'll find it interesting too. So stay tuned for, part 2 of this video and part 4 of this series, where we wrap everything up and we'll use everything that we've learned all the way up until now to actually get our backdoor written into this firmware and then repatched up and put on, so that, if this router were to be shipped back out, or we were to put it as an implant or something, when it boots on, it will actually go out and reach back to our command and control infrastructure. So again, I've been Digital Andrew. I hope you enjoyed this video. If you want to learn more about all of this IoT and hardware hacking, then please make sure you are subscribed. And I hope you have a great day, evening, night, whenever you're watching this.